Hey everyone, welcome back to Real Analysis 1. This will be lecture 14 of the course. And in this section, we're going to discuss continuous functions. So let's go ahead and jump into it. So we'll call this section 4.2, continuous functions. So in calculus, we've certainly come across this idea of continuity in calculus, and what we want to do here is firm it up a bit with a little more rigor and bring in maybe a more analysis, a real analysis-y kind of definition. But let's recall what we said about continuous functions from calculus. So in calc, I think probably calc 1, we say that a function is continuous. So we say that a function f is continuous at a point x equals c if all of the following are satisfied. So first thing we say is the function is defined at x equals c. Second, we have to have that the limit of the function exists at x equals c. Okay, and then finally that limit has to be equal to certain thing, and we say in particular that the limit as x approaches c of f of x equals f of c. All right, so if these three conditions are satisfied, we say that the function f is continuous at the point x equals c. And so this is all fine and dandy. This gives you a nice picture of what continuity means. But let's now define continuity from the standpoint of kind of the real analysis. Let's kind of look under the hood and see what's really going on here. All right, so here's our definition. Okay, we'll say let's let E be a subset of real numbers and f a real valued function with the domain being E. Okay. We say that f is continuous at a point P in E if, and here's the setup, for all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of p is less than epsilon for all x in the domain with x minus p less than delta. Okay, so basically what we're saying is a function is continuous at a point p if for all epsilon greater than 0, you can go find some delta such that whenever you're within delta of this point p, the function value is within epsilon of the point fp. Okay, and so that's the definition of continuity, right? So meaning you can get as close as you want to the point p, and you are less than epsilon. Okay. Kind of an alternative definition, another way to think about it is this. A function f from E into the real numbers is continuous at P in E if and only if, given epsilon greater than 0, there exists a delta greater than 0, such that f of x is in the epsilon, f of x is in the epsilon neighborhood of f of p for all x in the delta neighborhood of p and E. So kind of the same idea, right? Basically, f of x is in the epsilon neighborhood of f of p whenever x is in the delta neighborhood of p. Right, so kind of another way to think about it in terms of neighborhoods, if you prefer that sort of definition. Some people do prefer that sort of definition. I don't know which I like. I think they both are great, and they have their place, right? So now if we were to think about this kind of visually, what does this look like? Well, so let's just kind of draw an arbitrary function in here. There's your function f. And let's say we've got our point P here. Okay, and so we know that P is going to evaluate up here. This will be your f of P. Okay, and so if I have some kind of a delta neighborhood, so P minus delta, P plus delta, right? That's my delta neighborhood. And whenever I'm inside that delta neighborhood, I need to be inside a epsilon neighborhood of f of p. Right, and so this is what it looks like, right? So you're inside. To be inside of here, you just have to be able to find a delta that guarantees that you're inside of that range. Okay, so very similar to what we've seen with just kind of the idea of limits. Let's take a look at some examples, right, and remind ourselves how some of this works. Here's an example. Let's let g be the function x squared minus 4 over x minus 2 and 2. And so this will be a piece function. We'll say, well, this is when x is not equal to 2. Of course, it's not defined at 2. And this is for x equals 2. Now, just kind of thinking about what we say from calculus at the point, we would say at the point p equals 2, the limit as x approaches 2 of g of x equals 4. The limit exists, but it's not equal to g of 2, right? G of 2 is 2, right? The limit of this upper piece is 4, right? If you kind of think through this and kind of look at this, you can see that this converges to 4 as x gets closer and closer to 2. But the way the piece function is defined, there's this kind of a jump here, right? So there's a discontinuity. So g is not continuous at x equals 2. Right, this is kind of a simple example. Here's another example. This is a simple example, kind of reminding us what discontinuities can look like. Let's think about the function f of x equals sine of x. Now this is a function that we know is continuous on the real number line. All right, so let's show it. Let's kind of show that this is continuous using the definition. So we'll show that f is continuous on R. Okay, and so let's kind of start with just thinking about f of y minus f of x. And so we know that that is sine of y minus sine of x. Okay, and this can actually be rewritten if you recall back to your trigonometry. If you've taken it, the sine of a minus the sine of b is equal to 2 times the cosine of a plus b over 2 times the sine of a minus b over 2, right? So this is kind of an off to the side. And so that's what you have here, sine of y minus sine of x, so you can just kind of swap this in. And so this is equal to 2 times the cosine of y, I'm going to do it on another line. We'll go down here. 2 times the cosine of 1/2 y plus x times the sine of 1/2 y minus x. Okay, so sine y minus sine x is equal to this, and this is the identity that I'm using. Okay, and this is less than or equal to 2 times the sine of 1/2 y minus x. All right, now why is that true? Well, why is that true? Let's put a little note here. This is because the absolute value of the cosine of 1/2 of y plus x. This has got to be less than or equal to 1, right? Okay, so that being the case, having this additional term in here can only make this smaller, right? So we can pop that out, and we know that this whole thing here has got to be less than or equal to 2 times the sine of 1/2 y minus x. Okay. Okay, so we can note also that the sine function is bounded, isn't it? Just like the cosine function is bounded, the sine function is bounded between 1 and -1. So whenever we're close to 0, whenever we'll say h is approximately 0 or close to 0, then h is, the absolute value of h has got to be greater than or equal to the sine of h. Right? So this is true for really small angles, right? Whenever the angle is sufficiently small, then the absolute value of the angle is actually greater than or equal to the sine of that angle. And so this is basically what gets you to the finish line here. So we have f of y minus f of x is less than or equal to 2 times the sine of 1/2 of y minus x. And that's got to be less than or equal to y minus x, right? Assuming that it's a small angle. Okay? So this is kind of the algebra that you need in the background, right? So let's let epsilon greater than 0 be given, and we can choose delta equal to epsilon in this case. Then if 0 is less than y minus x, which is less than delta, we have that f of y minus f of x is less than or equal to y minus x, which is less than delta, which is epsilon, right? And so this is how we can reason about the sine function being continuous for all real numbers. Right? Anytime you've got two real numbers that are less than your identified delta, it will imply that the values of the sine function at those 2 points is less than the given epsilon. Okay. All right, so that's kind of a nice example of a function that we all know is continuous, and now we have proven it more rigorously. Okay. Very good. Let's take a look at a theorem. Okay, this is going to be one that we've seen from calculus, but maybe we'll take a look at it again. If E is a subset of the real numbers, and f and g are functions from E to R, and they are continuous at a point P and E, then we have the following. The sum and differences are continuous. So f plus g and f minus g are continuous at P. The product of the functions is continuous. F times g is continuous at P. And the difference, f over g, is continuous at P if g is not equal to 0 for all x in E. So basically that denominator has to be non-zero on the entirety of the domain. Okay. Very good. And these are easy to prove. You can basically prove, you don't have to prove these using epsilon delta. You can prove this just using some calculus. So I will leave that to you. And what I want to look at next, though, is one that isn't so easy, well, isn't as easy to prove, and that's the composition of functions. So let's let A and B be subsets of real numbers. And let's let f be a function from a to r. And let's let g be a function from b to r. Okay, so we've got a and b subsets of real numbers, and f is a function from a to r, and g is a function from b to r. And let's assume that the range of f is a subset of the domain of g, so it's a subset of b. So then if f is continuous at p in a, and g is continuous at whatever f of p evaluates to, then the composition g composed of f equals, let's call that h, that function h, that composition of g and f, is also continuous at p. Okay. All right. So I've basically got a composition of functions. So if f and g are continuous, and then g composed of f is continuous. Okay. And so let's prove this one, and this one will require, well, we'll prove it using epsilon delta kind of definition. So let's let epsilon greater than 0 be given. Okay, and what can we do? Well, since g is continuous, and we say continuous at f of p, by assumption, right? G is continuous at f of p. That means there exists some delta, we'll call it delta 1 greater than 0, such that, what do we got? Well, g of y minus g of f of p is less than epsilon for all y in the delta 1 neighborhood of f of p, and let's say intersecting the domain b, right? So basically, whenever f of p is inside the delta 1 neighborhood, or sorry, whenever y is inside the delta 1 neighborhood of f of p, then you have this closeness, right? Okay. So that's one part of it. And also by assumption, we have, and also since f of x is continuous at p, for this same delta 1, there's going to exist another delta greater than 0, such that what? Well, such that f of x minus f of p is less than delta 1 for all x in the delta neighborhood of p. And I'll say intersecting the domain A. Okay. Right, so you start by having an arbitrary epsilon given to you, and we know, given that epsilon, there's going to be some delta 1, right? And then that delta 1 gets plugged in as your next, you kind of think of it as daisy chaining these things. So given an epsilon, there must exist a delta 1, and then given that delta 1, there must exist a delta. And so these things are kind of linked together, right? And so what can we say in the end? Well, then, whenever x is in A, with the distance between x and p being less than this last delta, we would have that h of x minus h of p, which would be equal to what are, this is g composed of f, so this would be g composed of f of x minus g composed of f of p. This has got to be less than epsilon, right? And that's just the definition, right? So h is just a function, and this all kind of shows. So given an epsilon, you get a delta 1 greater than 0 must exist, and given that delta 1, you've got a delta that must exist. So all of these things are kind of shrunk down, and you get this daisy chain. So therefore, h is continuous at p. Okay, so that's a nice it's a nice proof. It's got some nice kind of moves, and there we go. So let's do a little bit of a shift here, and let's try to think about the idea of the continuity of a function, but more from a topological standpoint. So let's think about continuity from a topological standpoint, less from a epsilon delta calculus kind of standpoint, more from a topology kind of standpoint. Okay, and so the theorem that I'm going to give you next is, frequently kind of, you can think of this theorem as kind of the definition of continuity that you would come across if you were taking a more abstract version of this analysis. Like if maybe you were taking a class that was strictly focused on the topology of the real numbers, this is what you might come across as a definition of continuity. And so we'll state it as a theorem here. Okay, so let E be a subset of the real numbers, and let F be a real valued function. On E. Then F is continuous on E. F is continuous on E if and only if F inverse V is open in E for every open subset V of R. Okay, so let E be a subset of real numbers and F a real valued function on E, so E is the domain of F. Then we say that F is continuous on E if the inverse image of V, V being an arbitrary open subset of R, is open in E. Okay, so again, this theorem is frequently taken as the definition of continuity in topological coursework. So let's illustrate the theorem. Let's illustrate this theorem for a particular function. So let's think about this function, f of x equals the square root of x. And then let's say the domain 0 to infinity. Okay. So let's suppose that V is an open interval. So let's let V be an open interval. We'll just say AB. And then just with A less than B, right? Okay, and so think about, we've got f of x equals the square root of x, and so f inverse of x, you can just kind of do this work off to the side, we know is x squared. So kind of off to the side here, just keep this in mind. So what is the inverse here? Well, it's empty. The inverse image is empty if b is less than 0. Okay, clearly, right? Because the function is not defined there. And what do we get if, what is the inverse image of v if you've got a less than or equal to 0, less than b? So this image, this situation here, right? You've got 0, and we're talking about an interval that's below there. Well, the function is not defined there. But what about this situation where you've got 0 and you're kind of like straddling 0? So the function isn't really defined here, but it is up here. So what does the inverse image look like there? Well, it's 0 comma b squared, isn't it? Okay, just kind of thinking about what, so this is like your a and this is your b. Again, your a and your b. Okay. And then what about when the lower piece of the interval is greater than 0? So a is greater than 0. Well, in that case, you have this, don't you? Have the proper open interval, right? So that looks like this. Right? So in each of these cases, what do we got here? So clearly, we know that the open set is an open subset. Okay. Also, this is obviously an open subset. Okay. What about this piece in the middle here? Now, this piece in the middle is not open in R. So notice 0 comma b squared is not open in R. But is it open in the domain of the function? Is it? What is the domain here? The domain is 0 to infinity, right? That's what it's given. So let's remember what this what we had a theorem a while back talking about this very thing, and I think what we said then was, and I'll try to recall it here, u of x is open in x if and only if u is equal to x and some open set x, the intersection of x and O, for some open subset O of R, right? So remember this. Go back about 3 lectures and we came across this. Okay. And we can see that this is the case, actually, for this middle situation, right? Because notice that 0 comma b squared, right? This thing here, this is really equal to the intersection of negative b squared comma b squared and 0 comma infinity, right? And so this is like your u, this is your O, and this is your x, right? And so u of x is open in x, right? So this guy here is open in this set if and only if u is equal to x and O, which u is equal to x and O for some open subset of O of R. And so this kind of shows that according to that definition that we came across a few lectures back, this is true. So 0 comma b squared is open in 0 comma infinity, right? Right, so then basically what we're saying here is that if V is an arbitrary open subset of R, we know that, hold on. So if V is an arbitrary open subset of R, then V, of course, is equal to the union of I sub n, where I sub n is a finite or countable collection of open intervals. Okay, and we know that the inverse of V, this thing here, would then be equal to the union of the inverse of those open intervals. And each f inverse of in for fixed n is open in 0 comma infinity, right? So that's just what we just talked through, an example of that. Okay, so that implies that f inverse of v is open in 0 comma infinity. Therefore, right? So therefore f of x equal to the square root of x is continuous on 0 comma infinity. Okay, and so we're not going to prove this theorem. We could prove it. It's not beyond our capability, but just in the interest of time, we're not going to, and also because I think this theorem is, I mean, as I said, this is taken as the definition of continuity in more abstract courses. This is a plenty abstract course. We don't have to go all in on this definition, but just know that this is another way to think about it. And clearly it's a bit more abstract than the epsilon delta definition that we're running with. Let's talk about continuity and compactness next. Okay. So obviously there's several very important overlaps between continuity and compactness. And this theorem is a beautiful example. So if K is a compact subset of real numbers, and if F is a function from K to R, and that function is continuous on K, then the image of F under K is compact. Okay. So if K is a compact subset and it's also the domain of this continuous function F, then the image of K under F is compact. So this is to say that the continuous image of a compact set is compact. All right, so something about continuity takes a compact subset and maps it into another compact subset. So continuity is important for that. So let's prove this one. This is a little bit of a longer proof, but I think it's instructive and gives you some good ideas about how some of these things are related. Okay. And so because we're talking about compactness, we'll have to bring back the idea of open covers. And so let's let V sub alpha in A, be an open cover of f of k, right? So the image of k under f, right? And so if this is an open cover, really to show that f of k is compact, we need to show that a finite subcover exists, right? Okay, so this is what we'll start with. We'll start with the existence of some open cover here. Since f is continuous on k by assumption, we can say that the inverse of V alpha is open in K for every alpha in A. Right? This is the previous theorem. Okay, this is just that topological characterization of continuity. Okay, so f is continuous on K by assumption. That means the inverse image of each of these V alphas is open in K. Okay. All right. So then I'm going to flip pages here. So then for each alpha, there's going to exist an open subset U sub alpha, and this is a subset obviously of real numbers, such that F inverse V alpha is equal to K and U alpha. This is the same concept that we referenced in the last example. Okay. And so we claim that U alpha in A, is an open cover of K. Okay. All right. And let's see this. So if P is in K, then F of P is in f of k, naturally. And thus, we could say, therefore, f of p will have to be in v sub alpha for some alpha in a, right? For some, for one of them at least. Right? Okay. And this implies that P must be in F inverse V alpha, and therefore we would say also in U alpha, right? Okay. Now each U alpha is open. All right, remember that? Each U alpha is open. The collection U alpha, alpha in A, is an open cover of K, therefore. Okay, now K we know is compact by assumption. So that being the case, there exists alpha 1, dot, 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 alpha n, right, in this index set A, such that K is a subset of the union of these guys, U alpha sub j, alpha j. Okay, right, so we've got that, and this is all going to imply then that K is equal to the union j equals 1 to n of U alpha sub j and K. Right, and what is this? Well, this is just equal to the union j equals 1 to n of F inverse V alpha j. And, of course, right, so we can just evaluate both of these sets, and so we get that f of k is equal to the union j equals 1 to n of f inverse v alpha j. Okay. And what is this? Well, since f of f inverse of v alpha j is in v alpha j, we have that f of k is in the union j equals 1 to n of v alpha j, and that's what we needed, right? Fk then therefore must be compact, right? Because that's a finite subcover. Okay, and so that is a finite subcover. We've shown that the image of K under F is, so we started with an arbitrary open cover, and we can see now that f of k is actually contained in a finite subcover of that open cover. Okay, and so therefore, f of k, the image of K under F, is a compact set. Okay, very good, very good. So that's a nice kind of a tricky proof, but I think it kind of shows how a lot of these things are related, and that is, you know, those kind of proofs you have to muscle through sometimes just to sort of see these things. Now, what we want to do, kind of end on here, is the intermediate value theorem. Okay, and this is a theorem that, you know, you definitely would have seen in calculus, and here we can pull together a very nice rigorous proof of this. Let me state the definition again. So let's let f be a function from some interval ab onto the real numbers, and then we'll let it be continuous. Okay, and let's suppose that f of a is less than f of b. then if delta is a number satisfying f of a is less than delta less than f of b, then there must exist some number c in the interval between a and b such that f of c is equal to this delta. That's the intermediate value theorem. It's really straightforward, but I think if you remember back to your calculus, you'll recall that this was extremely useful, right? So I've got a here, we'll say, and I've got b here, some interval, right? And I've got some kind of a function that, you know, is defined on this interval. Okay, and so here's like my f of a, and then up here I've got what f of b is up here. Okay, now there's some gamma between f of a and f of b, right? So like right here. Okay, and so what this theorem says then is that if that's the case, if the function is continuous on this interval between a and b, so f of a to f of b, and there's some gamma between there, there must be a c in here, and namely right here, such that f of c is equal to delta. There must be some number in that interval ab, which when evaluated on f, gives you this gamma. Right, so that's the simple visual of the intermediate value theorem. Okay. So the way we're going to prove this is we're going to use our recent notions of continuity, but we're also going to use least upper bound property. Okay, and so let's prove this. All right. So the way we're going to start is we're going to start by defining a set. Let's let a equal the set x in the closed interval a to b such that f of x is less than or equal to, we'll say, delta. Okay. So thinking about it visually, it would be like all these guys down here, right? At some point, you know, there may be an element in here that is equal to this delta, but we're saying let's start by building this set out. Okay. Well, obviously a is non-empty, right? Because a is at least in a, right? The lower bound, we know that value. Right? F is defined on a to b, and we know that f of a is not equal to gamma. It's less than gamma. Okay, so we know that the set's non-empty. Okay, and since the set's non-empty, a is well, we also know, what do we know? That we also know that a is bounded above by b, right? Because f of b is greater than gamma, so this set a is non-empty because of the lower bound, and it's bounded above by the upper bound of the interval, right? Because f of b can't be equal to gamma. That's part of the theorem. F of b is greater than gamma, strictly greater, not greater than or equal to. Okay, so we've got a non-empty subset that's bounded above, and so this means there exists a least upper bound of a. And so let's let c equal the supremum of a. So the least upper bound of a is this number c. Now we can obviously imagine that based on how this set a is defined, this c is going to be the c that we're looking for, right? That the intermediate value theorem claims exists. Okay. All right. And so since b is an upper bound on a, c is less than or equal to b, right? So we have that also. Since b is an upper bound, we know then that c must be less than or equal to b. Okay, and as I just said, we wish to show that f of c is equal to gamma. That's really what we're after, isn't it? Right? This is the thing we're trying to get to. right? We need this information as well, though. B is an upper bound. C is the least upper bound. It must be less than or equal to B. Okay, so what can we say? Well, since C is equal to the supremum of A, then either C is in A or C is a limit point of A. That's true. Okay. Now, let's switch pages here. If C is in A, okay, let's see what happens. If C is in A, then f of C is less than or equal to delta. That's how A is built. And if C is a limit point of A, well, then there exists x of n, sequence in A, such that this sequence x of n approaches C, right? Because C is the supremum, right? Okay. All right. Since x of n is in A, x of n is in A, we know that f of x of n must be less than or equal to delta. Okay. Now, f is continuous, and therefore f of C must be equal to the limit as n approaches infinity of f of x of n. And that's got to be less than or equal to delta. Right? So in either case, right, if C is in A, then f of C is less than or equal to delta. If C isn't in A, but it's a limit point of A, then f of C has got to be less than or equal to delta. Right? We have the same thing. In either case, f of C is less than or equal to delta. Okay. So let's suppose, right? So what we'd like to see is that f of C is equal to delta. So let's suppose that f of C is strictly less than delta. Okay. Okay, so let's suppose that f of C is strictly less than delta. If this is true, then epsilon equal to 1/2 of delta minus f of C, that's going to be a greater than 0 value, isn't it? Right? Delta and f of C are not identical, so that's a positive value, and 1/2 of that is still a positive value. Okay. So obviously we're trying to derive a contradiction here, right? So since f is continuous at C, for this epsilon, there must exist a delta greater than 0, right? Since f is continuous at C, for this epsilon, there exists a delta greater than 0, such that what? Such that f of C minus epsilon is less than f of x, which is less than f of C plus epsilon. Namely, f of x is in the epsilon neighborhood of f of C. And this has got to be true for all x in the delta neighborhood of C. Right? Okay. Now, since we're assuming f of C is less than delta, C is not equal to B, and therefore this interval C up to B and the delta neighborhood of C, this is non-empty, right? But what's going on here? Right? But for any x in the interval C up to B, with C less than x less than C plus delta, f of x is less than f of C plus epsilon, right? And what is this? Well, this is just f of C plus 1/2 delta minus 1/2 f of c, just taking that idea of epsilon up from up above here, kind of plugging it in. And this is equal to 1/2 f of c plus delta, and we know that that's less than delta, obviously, right? And this is a problem because x is in A and x is greater than 0, and this contradicts the fact that C is the supremum. Right? You can't have all of this be true and also have x be in A, x greater than 0, and C equal the supremum of A, right? Okay. And so the whole thing doesn't work when we assume that f of c is less than delta. So f of c is equal to delta. Okay. And so that's the proof of the intermediate value theorem, using the ideas and the definitions that you get from continuous functions. All right, so we'll stop there for this lecture, and in the next lecture we'll discuss a finer point of continuity, and we'll specifically called uniform continuity, which is kind of an interesting idea. And then after that we will jump into monotone functions and discontinuities, and finally after that we will get to the derivative, and we'll define the derivative, and we'll be close to the end of our Real Analysis 1 journey. Until then, take care.